Okay, great.
Yes, we can hear you now. Yeah.
Okay, awesome.
Yeah.
So basically all I was saying was that our paper that we did our report on follows the presentation that we just saw. It's by the same author, and it follows this deep info max. So basically the structure of what we're going to be going over today is firstly, we're going to have an introduction and explain the goal of this paper that it proposed. Then we're going to do an overview of the local dim model, and then we're going to do an overview of the AM dim model, which is the model proposed in this paper. Then we'll go over a few different topics that the model covers, which is mixture-based representations, data augmentation. Then we're going to explain single-scale mutual information, which would belong to local dim, and then multi-scale mutual information, which is for AM dim. Then we'll go over the encoder of the model, and we'll go over some experiments. So firstly, the goal of this paper is to create a model that learns useful representations from unlabeled data in a self-supervised environment through maximizing mutual information between features extracted from multiple views of a shared context. So this is a lot of what we just saw in that previous report of the Deep Info Max network. There's a few additions, and it's implemented with this AMDIM, Augmented Multiscale Deep Info Max model, which is an improved self-supervised model to the local Deep Info Max model. So basically, to explain the goal, we broke down each little piece of that goal sentence that's up top there. The first part is learning useful representations. These would be representations would be features such as a cat's eyes, ears, and nose, and they'd be key identifiers in kind of classifying that image of a cat. And you can see our figure there on the right side. The next part of that sentence would be multiple views of a shared context. So in this case, a shared context is the single image, and the multiple views are different versions of that image. So you can see over there that there's augmented versions of the image that kind of are all part of the same thing. Maximizing mutual information is essentially estimating how similar or different two variables or sets of variables are. And in this case, the model recognizes the similar features that are shared with the views to kind of state that these two images are similar. And in self-supervised learning, the model learns from unlabeled data by using the data itself and its structure to create its own labels. Okay.
So I will explain the local deep, the mathematical part. So the goal in the local DIM is to maximize the mutual information between the pair feature F1 and F7. So F1 is basically from the output layer. We can see from the right picture, and the F7 is like the feature from the hidden layer. And our goal is to minimize the mutual information function under the joint distribution of F1 and F7. And before we start to minimize this objective function, we need to construct the joint distribution F1 and F7, and also the marginal distribution F1 and F7. So basically, we have the input data X image, and the data will have a distribution. Probably we don't know the distribution, but we can just randomly pick the image from this data, and the subscript ij also has distribution, actually following the uniform distribution according to this paper. And F1 as the global feature, it can summarize the high-level features like the cat ear, eye, and nose. And F7 from the hidden layer probably just represent one of the feature or just the background. Next. So go deeper, we can minimize this objective function. So to maximize this mutual information, actually is equivalent to minimize the loss function here. So the loss function is about the F1 and F7, and also the N7. So F1 and F7 actually is a positive sample pair from the joint distribution, and N7 is a negative sample from the marginal distribution of F7. And the key function here is the matching score function. Matching score will match the F1 and F7's similarity. And also this this value will be get from this phi function. So the phi function is like the embedding function obtained from the multi-layer perceptron network. Here, the task of the objective is to find the real F7, and so the higher matching score, that means higher likelihood of a positive sample pair found. And so to quantify this objective function, they also propose some calculation method to get the NCE function. So we see here is an expectation function here. So how to quantify the expectation function? Basically, we use the Monte Carlo. So we sample the data from the input image data set. So we can finally quantify these two expectation functions through the random sample here. So we can see this formulation. And eventually, the objective function will be represented by the F1 and F7. And the F1 and F7 basically are the weight and the bias and input X function. So eventually, the encoder will input the solution, the weight and the bias. But in this paper, they also mentioned some specific tricks. So they actually didn't just use this the matching score function. Actually, they added the regularization term here. After that, they use the soft clipping to round off the peaks. And then they use the tangent function. After that, they input the S prime to the matching score function, then get the NCE score. Next. So now I'm quick go through the extended model called Augmented Multiscale Dim. So basically, we have the vanilla local DIM and also extended model using the augmented data. So actually, the second formulation is for the single scale DIM using the augmented data. And we can see this picture here is for the second objective function. So we have F1 from the global feature vector, and the F7 X2 is from the hidden layer. And also, they also extend the model to fit for the multi-scale layer. So that means actually multi-scale actually is like multi-layers pair. So we can see in this objective function, they will compare the F1 and F7, and also F5 and F5, and also the F1, F5, F1, F7. So actually they extend the model from fit for F1, F7 to fit for 1 to 5 and F1 to F7 and 5 to 5. So this AMDIM will compare more different layers features to see their matching score, and also we can treat the matching score like the similarity. Next.
Sorry, could you please stop here a little bit and explain in more detail? Because like this is different from our the previous paper about this diff info max. So here actually you have this augment. So you have two techniques. One is compared to the previous one, you have the augmentation, and the second one you have this multi-scale augmentation.
Yep. Dr. Mo, we actually in the future slides we go into each difference between.
Yeah. It's
I
like
would like to compare
it will be explained in detail though.
Okay. Good.
Here I just go through the objective function and have a brief
this
overview.
Is just a quick overview. Yep.
Okay, good. Please continue.
Next. So also the author proposed a mixture-based representation. Actually, it's very related to the reinforced learning. So the objective function here, we can see the key part. So one is the Q function and also the NCE score. So NCE score can be get from the previous slide, the local DIM formulation. And here, the key part is the Q function. I think the Q function is like the posterior function for the F1 condition on the F7 feature. And also it's like the in the reinforced learning, like the policy function, and the tau is the hyperparameter. So eventually, this model, this formulation will be the F1 F7 features function, and the F1 F7 function will be the weight and bias and input X function. So eventually it will input the encoder F and also the policy Q. And so here actually I have some confusion why this paper so it's called self-supervised learning, but it connects to the reinforcement learning. And the author actually didn't provide the simulation result for this part, but we just want to go through this part and hope the professor can give some explanation. Yeah. Next.
So you mean the author only mentioned this method, but he didn't do some experiment based on this?
Yes, it's likely want to do it in the future work. Yeah.
Yeah, so I have no idea because I never read this paper by myself, so I don't know.
Yeah. Okay. Yeah. Nice.
So the author didn't provide any explanation about why.
He just mentioned the mixture-based representation, and they said it will take some time to tune the parameter, and after you tune, probably you can get a good result. He said it's a promising direction. They will probably do it in the future.
So from what I know, maybe because like they said, the idea is good, but I guess when they implement that, they didn't get some good result based on this.
Yeah, probably. That's why we didn't get it.
Yeah, it's like for RL, sometimes RL is really hard to train. So although like theoretically it can reach that point, but sometimes during some training process, the result is not as good as what we expect. So I guess maybe the author thinking maybe we can train in this RL method, but however, they didn't get some good result.
Yeah, they highlight the tuning the hyperparameters part. So they said probably we can get interesting result if we
but sometimes it's hard. It's like I when I did some RL method, so after we turn all the hyperparameters, the result is still not good. So it may relate it, as I said, maybe the reward, like they didn't set up the reward good, or the training method is not very well. So probably it's not only the hyperparameter problem, and we need to do more work in that direction.
Okay, thank you.
Yeah, and also did they put advantage of this? Like why, if they use the RL, what's the advantage of this compared to the previous?
So I just I think I know how to calculate the objective function, and because when the final objective function will be represented by input x and the weight and the bias, but I actually doesn't quite widely think using the reinforced learning can get a better result. So reinforced learning actually probably is not how to say doesn't rely the sample very much. They can search and they get the sample and recheck the reward. So yeah.
How did they define the reward? Could you please go back to the previous slides one more time? So how did they define the reward in RL?
Yeah, previous slide. I think the reward is the NCE score, because NCE score is like the higher matching score, the higher similarity. So the higher similarity, they think we found the match, and they can go next state. The next state probably is the next sample.
My question is why would they call this a reward? I mean, you can think of this like a target or like loss function. So why this is called a reward?
I mean, the NCE score, I think is reward, and because the Q is like the transition function probability, and that's why I think probably NCE score is a reward. And according to this paper, NCE score is to match the similarity between F1 and F7 pair of features. So if the higher matching score, that means the higher similarity found. So they treated the similarity as the reward, in my view. Yeah.
Okay.
And
so
and the AHQ is like the penalty. So like in the previous regularization term. So it's like the penalty here. So AHQ. So AHQ or alpha HQ is the it's like the penalty, in my view.
So could you tell me what is this SNCE? So it's negative sampling. So this how did they compute this S here?
NCE, I think the calculation way is like the previous slide I mentioned. So
I mean, do they
Kyle,
have a exactly function for this
yes,
SNCE? So I
yes,
mean, if they have a function, I would I'm not very convinced that this is called reward, because like when we
okay,
have some loss function, if you have this F1 and F7, if you can
yeah,
fit into a function called this SNCE, and we have a concrete function to describe that, usually we don't call this reward. We call it reward because like we interact with environment and environment give us a reward, and really hard to define the relation between the number, the reward you get with the input, right? So if we already
yeah,
have a function, you can just plug in the function there and get the result. The reward is when you interact, you don't know the function and you only get the result. So
yeah.
that's why I say I'm not very convinced that this is called like reward, because you already have a concrete function for this, right? So this
Yeah,
S.
that's why I also get confused because they
Yeah.
connect it with the software Q learning, and yeah, so it's reinforced learning part. So
Yeah.
this session, yeah.
Yeah, I'm very interested in this part, and I would like to read in the paper, like read in more detail about that. And I would also like you guys to look that in more details,
Yeah.
and we probably can discuss and write that like also the result in your report.
Yeah, sure. Yeah,
Okay.
thank you.
Yeah, please continue.
Kyle, you can, yeah, you can continue.
Thanks. So earlier in the presentation, we mentioned that there was already this deep info max model that they refer to in this paper as local dim, and this new model is augmented multiscale dim. And this is the first part of that name acronym AMDIM, the augmentation. So first, we're going to look at this local dim and AMDIM, these gray squares right here. So local dim maximizes mutual information between the features that they extract from a single unaugmented image. So if you look at kind of the bottom left-hand side of the slide here, you can see that image of a cat. So local dim just analyzes that image. AMDIM maximizes the mutual information between features extracted from many augmented views of the inputted image, which you can see right to the right of that image of a cat. That's what AMDIM uses to kind of learn the features of, in this case, a cat. So at the top of the slide, the AMDIM process. So what happens is the model takes that image of the cat, the original one, and they apply a random horizontal flip to the image. They just flip it randomly, and then they perform something called stochastic data augmentation on that image, which is just random forms of data augmentation, which we can see on the right-hand side of the slide there. The three that they mention are random resized crop, random jitter in the color space, and a random conversion to grayscale. So in our images on the left, we can see in that A of X set, there's the jitters in color space, and there's the different crops where those would all be images that would be analyzed. And you can kind of see how they could compare between two different images in that set to find an eye in both of them or an ear or something like that. So once they perform that random augmentation on the image X, they append that newly augmented image of X to a collection called A of X, which we're seeing down there. And then what the model does is it just performs a loop of randomly selecting two images from that set, which they call X1 and X2. They evaluate, the model evaluates the mutual information between that pair of images, and then it will select two new random samples from A of X, and it just repeats the evaluation. And that's kind of how the model learns those different features. And this kind of like, the reason why this is better than local dim is because if the model can recognize this like pattern of an eye or pattern of a nose, where it's always in different positions of the image or different color scales, it kind of further reinforces this model's ability to recognize those features in other images of cats. So it kind of helps with that generalization problem of not just learning the training data, but also being able to react to the testing data accurately. So the next part of the next extension that AMDIM introduces from local DIM is going to be multi-scale mutual information. But before I explain that, I want to explain what I call single scale mutual information. But this is essentially what local DIM did. So the technical statement is that local DIM maximizes the mutual information between a global output vector and a local prediction vector. But what this actually means is that the local DIM model, it measures the similarity between the outputted results from the classifier and the intermediate prediction results. So this would be like in a hidden layer, it takes a result vector from that hidden layer and it compares it to the outputted layer. And what this kind of does is it tells the network, kind of how it's doing in the middle versus how it should be doing in the end. And that kind of helps to have the model modify its inner parameters to get to the end result more quickly. I kind of think of this as like a sort of back propagation, but not really. It's kind of how I compared it in my head when I was trying to figure it out. This is kind of where that term local comes from, because it's like a local vector within that same route of classification on that image. And then deep info max, because it's deep in the network, they're maximizing the mutual information between the output and the hidden layer results. And so on the right, this is a figure that was used for to explain this kind of, where it's an example of the local DIM with predictions across two augmented views. Now, again, local DIM doesn't use two augmented views. They only use a single image, but the paper used these two augmented views for kind of just example purposes. But really what will be happening is they will be taking that green global summary vector all the way at the top and comparing it to that one square within that block of squares under it. The other thing with local DIM is that, as you can see in this figure, it's comparing this 1x1 space to a vector in a 7x7 space. And that's where this second main bullet comes in, where it's saying that the local DIM model is only capable of 1-to-7 mutual information maximization with, obviously, like I've stated before, a single unaugmented sample. So going from there to augmented multiscale.
So,
oh,
sorry, one question is, like you said, it can be like sort of back propagation. So why is like that? I think this is just back propagation, but back propagation is a training method, right? So why you said it's like
well,
sort
I
of?
was trying to, I'm not really an expert on back propagation either, but that's kind of how I was thinking about it in my head, because you're taking the end result and you're passing it backwards through the network to kind of compare it to the inner results, and that allows the network to refine. So it pretty much is back propagation.
Yeah, I think it's exactly this is like back propagation, right?
Mm-hmm.
Okay.
So now moving on to the improved version of this mutual information sharing or maximization within the network. The authors dubbed this as multi-scale mutual information. So this would be where the term multi-scale obviously comes from in the name Augmented Multiscale Dim. So as opposed to local DIM, which was maximizing information between that global output vector and a local intermediate vector, the authors state that the information now is maximized between antecedent and consequent feature pairs, which would be that pair of images X1 and X2, those two augmented views. But what this essentially means is that they're measuring the similarity between the output of X1, and then the intermediate prediction results of X1, and they're comparing those to the hidden results of X2. So as you can see in that figure to the right, not only are they comparing the output of X1, which is on the left, to the hidden layer results of X2, but they're also comparing the hidden layer results of X1 to the hidden layer results of X2. And they increase that previous 1-to-7 sharing to 1-to-5, 1-to-7, and 5-to-5. And so you can kind of see this there if you think of that 3x3 square as a 5x5. and that 5x5 square as a 7x7 plane, which they are because of padding, but they don't include the padding in this figure, which is why it's 2 pixels short. But you can kind of see how it's comparing across the networks, and basically what this does is it highlights those high level features between a pair of independently augmented samples, X1 and X2. So I kind of tried to go into this further, that if X1 and X2 both contain a cat's eye, but X1 is grayscale and X2 is resized, the model learns to recognize that pattern of the cat's eye regardless of the augmentation, which would be the position of the eye, color, scale, or size, etc., which further reinforces the model's capability to recognize that feature, the cat's eye, in other images of cats, which is, like I'd mentioned before, that generalization solution. Okay, now the third extension is the encoder. So basically, the way that the authors introduced this is by saying that, as opposed to local dim, the AM dim model implements an architecture with, implements an encoder with better architecture. They didn't really go into the encoder of local dim. They just went into the encoder architecture of this new AM dim model being proposed. So the first thing that they stated was that it was based on the standard ResNet architecture, but they made changes to that architecture to make it suitable for Deep Infomax. 2 main concerns that were listed, and these are kind of like those changes that they made to Deep Infomax. This was their motivation to do that. The first was controlling receptive fields. Receptive fields are kind of like, as an image is evaluated for features, like within a layer within the network, and it outputs a new image, kind of downsizing it to highlight the features. That receptive field is like that next layer. It's the image in the next layer. And so when the receptive fields overlap too much, that means like as a filter is moving through an image and capturing these different features, it can overlap and kind of share features, and that's not really good for what they're trying to do here, because if there's multiple high-level features in an image, like a cat's eye and a cat's ear, they may merge into one, and in this case, the model would not be able to recognize the difference between a cat's ear and a cat's eye, because it, due to overlap, always assumes that they're the same feature. The second concern would be keeping the feature distribution stationary by avoiding padding. And so basically they're aiming to maintain high-level features in an image as the image passes through the network. This can be seen down there on the right, where as the image, that figure on the right, where as an image is kind of processed, it may, lower in resolution, but those features need to still stay there so that it can be recognized. So there's solutions to the concerns. The first concern of controlling the receptive fields, basically what they did was, as you can see in those figures, and I'll just go back real quick, you can see at the top there of the green, those like little 1x1 squares. So there's actually quite a few layers that are 1x1 within the network. As you can see up in the top right, the algorithm, that's actually that is their like neural network. And you can see down at the bottom, they have some 1x1s right here, seeing that it provides F1. But the 1x1 layers are used in the network to reduce the overlap of the receptive fields, and it allows for each high-level feature within the sample to be represented independently. So this is again what we're talking about, where instead of taking a filter of like 5x5, they're taking a filter of 1x1. So they're definitely going to capture each single bit within that image, and they'll and then it's analyzed accordingly. And for keeping the feature distribution stationary, again, maintaining those features in the image, that's where they use mean pooling, which again can be seen on the right, where you can keep the standout features but still lower the resolution, rather than something like max pooling, where only the the highest level color pixels are maintained, rather than all of the pixel values as an average.
Oh, sorry, is this 1 by 1 layer? Is this 1 by 1 is a kernel size?
I don't think so because the kernel size, so you can kind of see right here, we listed out the parameters for both conv2d and resblock, which are the two functions here.
So
And
what
The
is
so
third
it?
one, yeah.
Yeah, so the third one is the kernel width. So it would be
Okay.
this value right here. And we actually tried to, we looked at this and we talked through it for, I don't know, I would say at least like an hour and a half, like just this little like thing alone, but trying to figure it out. And it just from what we can see, it's that they're just trying to reduce that overlap as much as possible in the convolution process so that they can, you know, keep all of those different features within the image, like eyes or noses, independent of each other, so that there is no overlap and the model doesn't think, oh, well, an eye and the ear are the same thing.
I'm thinking like if you don't want overlap, can you just make the stride larger so this one will not have no overlap? The stride of the kernel.
Yeah.
Yeah, I would say that would probably be that would be a solid solution.
Yeah.
They wanted to, one of the things that they mentioned, and we mentioned in the slide, is that they wanted to avoid padding. They still use padding in the model, as you can see there. It's
First,
yeah, the last variable. They do avoid it in the second layer, but in the first layer they do add a thing of 2, but that's just so the filter of size 5 can fit in the image. But yes, you're correct that if they wanted to avoid kind of overlapping, they would modify the stride accordingly.
And
So,
I'm still not very clear what is this 1 by 1 means. What does this 1 means here?
so the best way that I could visualize it was by looking at this figure right here, where it's kind of like that F1, where it's just broken down into a single like vector. It's kind of like the image is lowered in that resolution until they get these multiple feature vectors, or this single feature vector rather.
Okay.
Yeah, we you know, that's kind of one of those things that we go into more detail on our report.
Okay.
But for the presentation, kind of trying to overview it while going into it a little bit.
Sure, please continue.
Okay. So our last slide is a summary of the experiments that they outline, and Ren's going to go over those.
So the experiment actually is from the paper. We haven't done the code re-implement. So according to the authors, they provide 3 tables. So the first table based on the ImageNet and the Place 205 dataset. And the first 2 rows of result based on the fully supervised training way. And we can see the performance between the ResNet and also the AMDIM. So their difference is quite small actually. And also they also provide the unsupervised learning result based on the AMDIM. We can see at the bottom, the small and large. So the small means they use a shorter epichord schedule. Larger means they use a larger epichord numbers. So we can see the epichord, the number of epichord actually after the accuracy of the classifier. And in the middle, they also compared with other competing methods from other reference, probably a 7 method. So all those method results cannot outperform the EMDM. And in the second table, the author used the dataset CFAR10 and CFAR100, and also they present the result from highway network and ResNet and wirelessNet. So those are all fully supervised learning methods, and they got this result. And AMDIM, here they trained on self-supervised way. So their result actually can competing with the fully supervised result, and it's very impressive. That means in the future, we don't need to label the data because we don't need to label data, and we use the unlabeled data, we can get a good result competing with the fully supervised result. And in the third table, they use the dataset STL10 and ImageNet. And here, actually, they also want to compare the different data augmentations effect on the result. So this one AMDIM result actually is based on using other data augmented skills. And here they list each type of data augmentations result here. And among of them, the strong augmentation actually has the best result. So the strong augmentation is like reduce some mutual information between the views, but still keeping the task relevant information intact. That's my understanding. That's why they got a very good result here. So actually, the strong augmentation get the best result among other augmentation ways. Yeah. So that's the experiment summary.
What is this stabilize means?
Stabilize actually is also a type of the data augmentation way. So it's like, let me see, let me check. I think they mentioned, so it's like the, so it says stability regularization and yeah, stability regularization, they mentioned it.
So what does it mean? So stability regularization.
I think that, so what I,
something like that.
yeah, so kind of what we were, what I read from this was that they're testing the accuracy of the model when they get rid of different data augmentation methods, but also when they get rid of different mutual information maximization strategies, which would be those two at the bottom there, that multi-scale and that stabilize. So the three color jitter, random gray, and random crop, those are the three strategies that we outlined in the data augmentation slide. But those two, multi-scale and stabilize, are obviously the this multi-scale thing right here. And then I believe it's this stabilize of controlling the receptive fields. That's kind of what I read from it.
Okay.
And yeah, so when they kind of got rid of that part.
Try to go back to the paper and make this clear, right? So
okay,
and that part, and also like in the second table here in the middle. So you said like when they compare this AMDIM with other supervised learning, like for example, ResNet, highway network. So are they training this in this way? So they first use this DIM to learn the representation, and then they also train it as a supervised in a supervised learning manner, right? So they don't do this totally unsupervised, I guess.
So the AMDIM, they trained actually also self-supervised way and a fully supervised way. Yeah, they trained actually it's two way, I think. Yeah.
I think that from what I know, so like they should do this in a two stage. So in stage one, they learn the representation with this AMDIM, and after they learn the feature, I think they will fix the parameter of the like some steps like until like all the parameters, and then they use the feature they learn as an input vector for a linear, like you see, I see they write linear and MLP.
Yeah.
So I guess after that they train it with linear and MLP, and training this one with a supervisor. They use a label to train the linear and MLP. I guess this is like they do that in a two-stage training, but make this clear, right? Go back to the paper and double check that and make sure like how did they train it? Because like if they want to compare this with supervised learning, right? So they also use label. They just use this method to learn the feature, and after they learn the feature, they still need the label to train it. Otherwise, how can they compare this one with other supervised learning? It's not very fair to say unsupervised can have similar like result as supervised. No, I don't think we should make that like draw that conclusion, because even this one, when they compare, this is still a supervised learning. It's just that we have a two-stage training. That is what I thought, right? Okay. Overall, it's good. Yeah. So
Yeah, Professor, I have a question. So here,
Yes.
they mentioned the linear and MLP. So MLP, I know what that means, like they train a
Yeah, I think it's just a
network.
multi-layer perception
Yeah,
with linear
but
activation function, I guess.
so the linear evaluation is just like a linear activation function.
I think
Okay.
it's linear
Yeah.
activation function. Yeah, it's usually like that, but double check if they make some comments in the paper. But I